Okay, so we'll conclude the discussion of single dish radio astronomy today. And the talk is going to be fairly short because I have a meeting at 2:30, unfortunately. So I may have to stop you from asking too many questions, which I'm sure will not stop you, but we'll do our best to stay within 2:30. If you have more questions, just email them to me, or you can ask them later. I mean, Desh, for example, is certainly much more of an expert than I am on single dishes. Again, we'll do a brief recapitulation of what went yesterday, talking about the various characteristics of one, the power that you receive from the sky, and two, the characteristics of single dish or dish antennas, the things that determine their sensitivity. And then we'll move on to the stuff that I missed yesterday, single dish. Well, I talked about single dish calibration. And so we'll again go through that because that is relevant to the calibration that I will talk about. And finally, I'll give you an example of this calibration, talking about calibrating the Green Bank telescope for spectroscopy. So this is what we did yesterday. We first, we defined a quantity specific intensity, which is basically the power received per unit area, per unit solid angle, and per unit frequency from the sky. And this quantity is often called, or is also called brightness. And this has units, and it's important to remember these units because a lot of people mistake or interchange intensity and flux density. Flux density is obtained by integrating the intensity over the solid angle. So the units of specific intensity are watts per meter square per hertz per steradian. And it is especially relevant for extended sources. Flux density, on the other hand, is the power received per unit area per unit frequency. And this has units of watts per meter square per hertz. I'm not sure why I have, I beg your pardon, there's an extra second S floating over there, which is not correct. I think that's where I subtracted, I erased SR -1 and left an S accidentally. It's watts per meter square per hertz, ignored the S. But because radio sources from the sky are so faint, we have invented a new unit called the Jansky, which is 10 to the minus 26 watts per meter square per hertz. And I also mentioned that even a Jansky is actually a very bright source. A source which has a flux density of 1 Jansky is quite bright. Today's radio interferometers, for example, like the GMRT or the JVLA, have make images which have RMS noises of a few micro Jansky per beam. I believe the deepest image with the Meerkat telescope has an RMS noise of less than a micro Jansky per beam. So, which is 1 million times fainter than 1 Jansky. So that tells you that even a 1 Jansky source is very bright in terms of our sensitivity today. The next two things describe the characteristics of a telescope or of an antenna. And the first thing which determines pretty much the noise properties of the telescope is the system temperature. And this is a sum of the noise power contributions from all the electronic components in the signal path and the sky, the actual source and any background and the microwave background and the atmosphere and any scattering that happens from, say, for example, the feed legs and any pickup and pretty much anything else. For example, broadband interference could raise the system temperature. And so the definite ones that you will have which contribute to system temperature are first the receiver temperature, which you can reduce to as low a value as possible by including a low noise amplifier very close to the feed, which bumps up the signal while not adding much noise. The sky temperature, which as we mentioned is very important at low frequencies, less than about 500 megahertz, but is not that important between say 1 and 10 gigahertz or higher frequencies. The atmospheric contributions to the system temperature, which as we mentioned are very important at frequencies above about 20 gigahertz, but are not important typically between 1 and 10 gigahertz or lower frequencies. The scattering from the feed legs or any blockage between the dish and the feed. And this is extremely important, or this is important for things which have feed legs and say on-axis feeds, but especially feed legs. But this term is the term that goes away when you have an unblocked aperture like the Green Bank telescope. So as I mentioned, the Green Bank telescope has a system temperature of about 18 degrees Kelvin at L band at 1420 megahertz, 16 degrees Kelvin at 5 gigahertz, while, for example, most other telescopes in the world, the VLA, Arecibo, the old Arecibo, FAST, and so on, has system temperatures of about 25 to 30 Kelvin at 1.4 gigahertz. So about 8 to 10 degrees Kelvin higher than the Green Bank telescope. And that is roughly the contribution from the T scattering term. Then there's ground pickup, because the ground itself radiates like a black body, or approximately like a black body. And so if any part of your feed is looking at the ground, then you would pick up some temperature from the ground. The side lobes, for example, of the response are looking at the ground, you'll pick up some contributions to the ground. So all of these contribute to your system temperature. And your aim when you're designing a dish is to minimize your system temperature. Because as you'll see in a minute, your signal to noise ratio contains the system temperature in the denominator. And so your signal to noise ratio is increased if you can minimize your system temperature. The thing that matters, the other thing that matters for a dish is the gain of the antenna. And the gain is defined as AE, the effective aperture, divided by 2K, the K is the Boltzmann constant. And AE is basically eta times A, where eta is called the aperture efficiency, and A is the geometric area. For typical antennas, eta is about 0.6, 0.7, and A is the geometric area. And this basically gives you the increase in the system temperature because of the target source. So it's a small increase in the system temperature because of the target source's flux density. And the measured antenna temperature because of the target source is basically this gain, AE by 2K, multiplied by the flux density of the source. It's a fairly simple thing. So this is the signal, AE upon 2K multiplied by S nu, where S nu is flux density of the source. And the RMS noise, we went through that yesterday, for a given integration time of delta t seconds and a bandwidth of delta nu in hertz, is given by sigma is equal to T sys upon delta t delta nu to the power half. And this just comes because of independent samples. A square root of 2 times T sys is the noise on one of those samples. And so then the signal to noise ratio is simply the ratio of this signal to this noise, which is AE upon 2K T sys. So this describes the antenna itself, AE upon T sys, multiplied by 1 upon delta t delta nu to the power half. This describes the observations, if you like. So for example, I could observe for longer, and that would improve my signal to noise ratio, but it only goes like delta t to the power minus half. And I could use, for example, for continuum observations, a larger bandwidth, and that will again improve my signal to noise ratio. For pulsar observation, I could use a broader bandwidth. For spectral line observations, unfortunately, your delta nu over here is going to be limited by the line width. You can't go broader than line width, otherwise you're not adding any signal, because the signal itself is narrow band. So therefore, for continuum and pulsar observations, increasing delta nu improves your signal to noise ratio. For spectral line observations, the maximum delta nu is typically half the line width, so that you have two independent point measurements across the line. And then finally, you have the flux density of the source. For a higher flux density, of course, you get a higher signal to noise ratio. So that is what we talked about as background for telescopes yesterday. Moving on to single dish calibration, the way you calibrate a single dish is that you measure the antenna temperature. And I've said arbitrary units. That's not quite right, because what you will do is to measure the second one first towards the target source, which I've called T on, which is this is just like an uncalibrated measurement of numbers of the noise power in some arbitrary units, and towards nearby cold sky. And in such a thing, towards nearby cold sky, this is called position switching. Alternatively, you could measure the off temperature at a nearby frequency, not on the same source, but at a nearby frequency. The first of these, where you observe an off position on the sky, is called position switching. The second of these, where you observe the same source but at a different frequency, is called frequency switching. And then what you do is that you simply say that, okay, the T source is T on minus T off. T on is basically, it's a T sys plus the temperature added by the source minus T off. So obviously this thing is basically the antenna temperature divided by T off multiplied by T off. So this is almost a triviality, but the point is that this can be measured. So as long as if I know the value of T off in Kelvin, then I can determine T source. So the question is, how do I measure T off in Kelvin? And the way you measure T off in Kelvin is simple. You just put in a noise diode of a known temperature. And this is where you actually get a number, so to speak, coming in. And you get T off by essentially a very similar equation. T off is just noise off divided by noise on minus noise off multiplied by T cal, where you know the calibration temperature. You know the temperature of this noise diode. So now having done this, you get T off. And then you plug T off in this equation, measure the power on the source and the power of the source, and you get this quantity, and then you get the source temperature. And then if you know your effective aperture of the antenna, and hence the antenna gain, you simply infer the source flux density by saying that the T source is 2A is AE divided by 2K multiplied by the source flux density. The way you get the antenna gain is by observing calibrator sources of known flux density, which have already been calibrated earlier. And so somebody has to do the work of determining the true flux density of these calibrators. And there are a handful of calibrators known, about 10 or so calibrators that are known with reliable estimates of flux density at about a gigahertz, let's say. And if you really want to get accurate flux density measurements, then you have to worry a lot, for example, over the variation of the flux density of calibrators with time. How well do you know the calibrator flux densities and so on? So that's the way you calibrate a single dish. And again, let me emphasize, these are two approaches. One is position switching, where you measure the off temperature by observing a nearby position at the same frequency. The other approach is frequency switching, where you observe the same source at a nearby frequency. And these are done depending on circumstance. So for example, if you're doing 21 centimeter line observations in the Milky Way, where every direction contains 21 centimeter emission, then you cannot do position switching. You're forced almost by fiat to do frequency switching. You're also forced to do frequency switching if you're observing a really bright source. For example, like say the galactic center, such as A star. And frequency switching is normally done for spectral line observations. Normally, but not always. So let's move on now to calibrating the Green Bank telescope. And so this project involved a search for 21 centimeter emission from a dwarf starburst galaxy. Very faint object, a small galaxy. It had never been detected before in 21 centimeter emission. And we had about an hour of time. The source is extremely bright in HST images. And so we wanted to see what were the gas properties like. And the 21 centimeter emission signal can be converted into the H1 mass of the galaxy. So it would allow us to estimate the H1 mass if we can detect the 21 centimeter emission signal. And this object is somewhat far away. It's not very close by. So, and it's a dwarf, so it wasn't clear that we could detect it. But, you know, it's a slightly redshifted system. You'll see the redshift in a minute. And so therefore it was possible to calibrate via position switching. And we did a fairly standard calibration, 5 minutes on source and 5 minutes off source. So you spend 5 minutes with the telescope pointing at the source, 5 minutes with the telescope pointing off the source. And the reason you do this is that it actually takes about 30 seconds to move from the on source position to the off source position, and then 30 seconds to come back again. Which means that for every 5 minutes you spend on source, you are spending 5 minutes off source plus 1 minute of slew time to go back and forth. So for example, suppose I did only 1 minute on source and 1 minute off source, which would probably give me better calibration. Then I will spend 1 minute on source, 1 minute off source, and 1 minute to go back and forth, which becomes extremely expensive. I spend most of my time in slewing. And so that is the problem in such calibrations, that you need to worry about how much of time are you spending on the calibration and how much of time are you spending on the source, because the source time determines your final sensitivity. In this delta t, in the delta t over here, this delta t is the on source time, not the total time. And so that is an important thing. So for example, you know, if I spend 1 minute on source, 1 minute off source, about 66% of my time is being spent off source and only 1/3 of the time on source. Here, what's happening is that half my time is being spent, roughly half my time is being spent on source. And so I get a slightly higher signal to noise ratio at the cost of slightly worse calibration. And we did 6 10-minute scans, about 1 hour in all, in fact, 1 hour and 6 minutes because of the slowing time. And so this is what we got. This is the raw spectrum. And if you kind of peer at it, you see that the scale over here, this is about 1 times 10 to the 8, sorry, 10 to the 9 over here, 8 times 10 to the 8, 6 times 10 to the 8, and so on. So each number, each big interval is 2 times 10 to the 8. And this is a completely arbitrary count. So don't worry about what that means. Some arbitrary scale. And you see that these numbers don't have any meaning. The system temperature is written as 1 Kelvin on the top. And this is one polarization only. And of course, we observe with 2 polarizations. This had a frequency of 1407.6 megahertz, 1.407 gigahertz. The bandwidth was about 23.4 megahertz for these observations. And it says over here, this is non-off observing run. So then we calibrated using the same, using this approach, where we basically got the T source via this, and we used the TCal measured to get the off source temperature. And this is what we got. So this is now the antenna temperature in units of Kelvin. And so the calibration temperature was 1.46 Kelvin. And from this, we could measure the T-sys. And the T-sys was 17.02 Kelvin. Extremely low, as I mentioned. This is the Green Bank telescope. So it's a unblocked aperture. And you can see this is very slightly below zero, which kind of says the calibration has not really worked perfectly. The central value is below zero. The reason that you're not seeing a positive value for the antenna temperature is that this source is a dwarf galaxy. It doesn't have any continuum emission. It has no broadband emission. We are searching for a spectral line, but the object does not radiate or does not radiate much in the continuum. So therefore, the average temperature basically is close to zero. And because the calibration is not quite perfect, it comes out the average temperature is a little bit less than zero, but by a very small amount. So now we convert this temperature into a flux density by multiplying by the antenna gain. And the antenna gain was already known to us before the observations, but we also measured the antenna gain towards a calibrator source, which was in this case 3C286. And so we went and looked at 3C286, measured the antenna gain, and this gave us a flux density. And it turns out that the antenna gain for the GBT at this frequency is about 2 kelvins per Jansky. So the effect of this conversion is just to divide each number by about a factor of roughly 2, I beg your pardon, by a factor of roughly 2. So you can see over here that this is about minus 0.1, and then this is about minus 0.05. That's roughly what's been done. It's not exactly that, because the gain is slightly different across as a function of frequency, but approximately this is correct. What you also see is that there are low-level wiggles in the spectrum. Not absolutely certain, but there's definitely kind of an oscillation that goes, there's a slight rise in the spectrum over here. So the bandpass calibration has not been perfect. We didn't care too much about this because we were interested in a very narrow spectral range, just about somewhere over here. So we're going to zoom in on that region. And so that is the calibrated spectrum for a single polarization. And then what we did was that we simply took all of these spectra from all the scans, all the 6 10-minute scans. We took both polarizations, and then we also averaged in frequency. And that's what we got. So we averaged the spectra from all 6 scans, we averaged both polarizations, and then we smoothed by 11 channels. We're actually originally smoothed by 2 channels already. So 22 channels was the smoothing. And this is what we got as our final spectrum. So this is now the frequency range that we are interested in, which, as you can see, is much narrower. So we started over here at about 1396 megahertz and went to 1420. And here I'm plotting in a zoomed in range, which is more like 1402 to 1409 megahertz. And you can see this beautiful spectral line sitting out over here. It's quite weak. It's only about 5 millijansky, 5.5 millijansky strong. It's very narrow, as you can see in frequency. It's not even, it's less than a megahertz wide at full width RF maximum. But you can see that the spectral baseline is really nice. It's basically just got noise over here. There's no evidence of oscillations over about a 10 megahertz frequency range. So this is an example where the bandpass calibration has worked quite nicely. There's been no problem at all. For example, if there were oscillations in the spectrum, it went up and down over here, you wouldn't be sure whether the flux density were actually this, or if that spectral line is sitting on top of a ripple or at the bottom of a ripple. So here, this thing has worked quite nicely. And the line flux density is about 5.5 or so millijansky. This kind of gives you a feeling for how weak spectral lines can be. And of course, it can be much weaker than this. This object is a dwarf galaxy at a redshift of about 0.012. Not very far away, but not very close by. Remember, it's a dwarf galaxy. So that's basically all that I wanted to talk about today. And fortunately, there have been no questions. Now we have time for some questions, if you like.
All right.
So I had a question from the first class. So yeah, so in there we talked about the secondary focus, right? So we discussed that the large reflector of the secondary focus would kind of block low frequency radiations coming up. So, I mean, won't that block higher frequencies as well? Like, why is it only exclusive for lower
because the
frequencies?
size of the reflector is a function of the wavelength. If the wavelength is smaller, you need a smaller reflector.
Oh, okay. So
That's
that's
all.
why the larger ones block
Exactly.
lower frequency ones.
Yeah.
Okay.
So I had a question about the type of structure present in GBT,
Yeah.
which is somewhat different from other single dishes, right?
Yeah.
So I want to know if there are any drawbacks to this, because most of the other telescopes, if I know correctly, are of the other structure, not this one.
Yeah. It's very expensive. That's the main drawback.
Expensive to construct.
Yeah. I mean, in cost.
Okay.
That's
Okay.
basically all.
Okay.
But it's just much better. The problem usually is that when you're building telescopes, you have to worry about how much money something will cost, and then you have to put in you decide whether you spend the money that you have. You don't have an unlimited amount of money, so you always make compromise the decisions. The GBT, remember, is the youngest of the telescopes that I talked about. All the other telescopes, Arecibo was built in the early 60s. Effelsberg was built in the mid 60s and came online in the late 60s, early 70s. So GBT was came online in 2002, 2001. So GBT is a very modern telescope, and that's the reason that many decades of experience have gone into the GBT. And now the GPT, but it's still expensive to if you were building another single dish, you would think deeply as to whether you really want to do this, because the cost goes up like mad. And the GBT's design has actually now been implemented, as in the off-axis unblocked aperture design, has been now implemented in the MeerKAT telescope, and will be implemented in the square kilometer array, which are interferometers.
That's very interesting. Thank you.
Sir, could you explain the last point again, like average spectra from all scans and both polarizations? That point, could you just...
Yeah. So over here, this is a spectrum from one polarization and one scan, right? Now, remember I said that your noise goes down when you average independent measurements.
Yeah,
right?
Yes,
so each scan gives me an independent measurement of the spectral line. Each polarization, the spectral line is unpolarized. Each polarization gives me an independent measurement of the spectral line. So now if I average the spectra of all scans and both polarizations, my signal noise ratio, my noise goes down by square root of 12, right? Because these are 12 independent measurements.
Yeah, yes, sir.
Right? And then it turns out that when we observed with a very high spectral resolution, mostly because, so when you're observing at these frequencies, you really want to worry about radio frequency interference, narrowband RFI. And if you observe with a high spectral resolution, then you can often localize the RFI in the spectrum, remove just that channel, and then later on smooth to the resolution that you want. While if you observed with a coarse resolution, then the RFI will affect all the channels. And so what we did is that we observed a lot of channels, and then we smooth the channels to come to this resolution at which we search for the line. We would like to have a spectral resolution such that we can at least see a couple of at least 2 points above the full width Raf maximum, and here we can see about 4 points above the full width Raf maximum.
Yes, sir. So this both
same scale.
Sorry, what?
No, sorry. Please go ahead, Lakshmi.
Yeah.
Yeah, sir. I mean, both polarizations in the sense like, what are the both polarizations which we are considering?
Oh, I see. So over here, radiation can be polarized in 2 orthogonal directions.
Oh, okay.
Right? And any antenna or any feed is only sensitive to one of these polarizations. And so what you do is that you design your feeds to be sensitive to both polarizations, and that gives you 2 independent measurements of the signal. For a polarized signal, and that allows you to even measure polarization in the sky. The way we talk about this in the school. But for example, in the case of unpolarized radiation, where all you care about is the intensity, then you simply average both polarizations and you get the Stokes the intensity.
Oh, okay, sir. I got it.
Desh, you were saying something?
Yeah, I just wanted to compare this 6 millijansky peak
Yeah.
On the scale of the raw spectrum, just to drive home the point of how much improvement has come about.
You mean this one or the?
No,
or
the one, yeah, the calibrated one.
Yeah. Yeah. So you can see that here the peak to peak is something like some number like maybe 80 millijansky. This is in Jansky. And the lowest number here is about minus 0.08, minus 80 millijansky. The highest number is about maybe 30, 40 millijansky. Just say 120, 110 millijansky. And when you look over here, the peak to peak is about plus minus 3 millijansky, let's say. The peak noise spike is about 3 millijansky and the peak negative is a minus 3 millijansky. So you can see that the peak has gone from, the spread has gone from 120 millijansky to about 6 millijansky. And that has come because of the averaging that's been done and the smoothing that's been done.
Yeah, thanks.
Yeah.
Sir, what is the physical significance of negative flux density?
Which negative flux density?
Here, like in the plot, yeah, it goes
over here.
This one, yeah.
Oh, you mean these things?
Yeah, the thing.
Oh, that's just noise. Noise
Okay,
can be yeah. It's just noise.
Okay.
Noise has a zero mean, and so it can have positive and negative values.
All right.
You're subtracting out any continuum from the source, and that will give you a zero mean measurement. Okay, I think we probably have had, people are probably thoroughly sick of me by now. So I should probably stop then. It's also 2:30. So then maybe I'll stop. And in case anybody has any more questions, please feel free to write to me. My email address is nkanaker@ncra.tir.in. And if you have any other questions also, not just about single dishes.
Thanks a lot, Nissim.
Nissim.
Yeah, any questions, we'll forward it to you too.
Okay.
Thanks for taking the extra time as well. Thanks.
Okay, so good luck everybody. Yeah, bye for now.